Hey everyone, in this video let's take a look at question 261, graph valid tree on Leetcode. This is part of our blind 75 list of questions, so let's begin. So this question is actually a premium question, and that's why we're doing it on the Leetcode website and why the number here is different, but otherwise the question, the test cases, and the solution are the same. So let's take a look. So in this question we are given n nodes labeled from 0 to n minus 1 and a list of undirected edges, which means each edge is a pair of nodes, and I want to write a function to check whether these edges make up a valid tree. We can assume that there are no duplicate edges will appear in edges, since all the edges are undirected. 0, 1 is the same as 1, 0, and thus will not appear together in the edges. Okay, so what does this mean? So let's take a look. We'll go ahead and copy these examples here. And again, this website is where we will do our premium problems because they allow us to do them for free. We will do them here. Okay. So it looks like we're given an adjacency list to start off, and the graph is undirected. And what we are asked to do is determine if this, based on the adjacency list, if this graph is actually a valid tree or not. Now, what is a valid tree, right? Because they haven't really told us what is a valid tree. So I'll just go ahead and tell you what is a valid tree. So a valid tree satisfies two conditions, first of all. It satisfies, I guess, a couple actually. It satisfies, first of all nodes are connected. And I'll explain what that means in a second. It also satisfies that there are no cycles. Okay, so what does this mean? Well, what it essentially means is that let's say we had 3 nodes, right? Let's say we had 3 nodes. Oh, take a look here. Okay, so let's just say we had 3 nodes, right? We had 3 nodes. What does it mean, first of all, that all the nodes are connected? What does it mean? Well, it means that from any node, you could visit any other node. So what it means is that from this node over here, and maybe we can give these nodes names just to kind of make them easier to understand, it means that you can reach any node from any other node. So basically, something like this, right? This is an entirely valid tree. Why? Because it is connected, first of all. And you might ask, how can we reach like 2 from 3, right? Well, notice that these edges are undirected. So really, if you want to kind of think of this in terms of a directed graph, this would kind of be like an edge here and then an edge over here. Similarly, an edge here and then an edge back here. You can kind of think of it as that one. Okay, so we now understand that the graph is connected. Now, what about the second point? Well, it means that there are no cycles. So what does it mean when there's no cycles? It means that we don't have anything like this. It means that we don't have anything like this, a cycle over here. Because what this would mean is like we could just infinitely go maybe somewhere here and then back here and then back here, etc. There should not be any cycles. You still should be able to visit every node from every other node, but there shouldn't be any cycles. And to add on to kind of like the first point about the graph being connected, an example of an unconnected graph would be something like this. Like, let's suppose we don't have these 2 connections over here. So then what do we have? Well, we have 3 nodes, but from 1 we can only reach 2, and from 2 we can only reach 1. We cannot ever reach this 3. So in this sense, the graph is unconnected. Okay, so we have these 2 pieces of information that make a valid tree. Now, you might ask that if the tree, if the tree over here is actually undirected, then it means that there are cycles, right? Because if you think about it, we'll have an edge over here and we'll have an edge like kind of like also back here. So there are cycles here, right? Well, technically there are cycles, but when we are approaching this problem, we're not going to refer to this as a cycle. So if we see an undirected edge, we will not, for example, from 1, if we visit 3, then we will not visit 1 again. Because technically, although this is a cycle, the graph is supposed to be undirected. So technically, this is not a cycle in this case. So we're not going to be thinking this in terms of a directed graph, but in terms of an undirected one. But when we're doing our coding, it will still be in terms of a directed graph, but we will make it clear that this is not a cycle. So that's just one point I wanted to point out, first of all. Okay, so if you think about it, the only thing we really need to calculate or you need to determine is that these 2 conditions are true. If they are true, then I know that my tree is a valid tree, or my graph is a valid tree. Otherwise, it's not. So it's actually easier to determine the opposite. So we will determine if all of the nodes are potentially not connected, or potentially if there are any sort of cycle. And if any of these conditions is false, then I know that it's not a valid tree. Okay, so how might we go about doing this? Well, let's take a look at this first example that we have here. I've actually drawn it right over here. So we can see that 0 is connected to 1, and then technically 1 is also to 0, but I'm showing it as an undirected edge here, and then 0 to 2, and then 0 to 3, and then 1 to 4. We can see here that all of the nodes are connected. From any node, we can visit any other node. We can also see clearly that there are no cycles. Now, what can we understand from this? Well, we can understand that if we were to traverse through our tree, and maybe we did our DFS call, maybe we did our DFS call from this node over here, this 0 node over here, what can we understand? Well, we can understand that we can reach every single node, right? And really, it doesn't matter where we do our DFS call from. We could maybe even like do it from over here. But if the graph is truly connected, then what it means that from any one of these nodes, we should be able to visit any one of these other nodes. So really, if I do a DFS call, then I should be able to visit 1, 2, 3, 4, 5 nodes. And it doesn't matter like where I do it from. I could do it from the 3, I could do it from the 2, or just maybe do it from like one of the indices. Because for example, if it wasn't connected, maybe if this edge wasn't there, then from any of these, if we did it, then we would just be able to visit 4. Maybe if we did it from here, we would just be able to visit 1. But we would definitely know that we would not be able to visit 5. So in that sense, we can just do it based off of just one of the nodes. We don't have to go through every single node when we're doing our DFS call. Okay, so that's one thing. That's one thing we know. Now, what is another thing we know? Well, another thing is that we want to make sure there are no cycles. So how can we make sure there are no cycles? And that actually seems to be the problem in the second graph. In the second graph, you can see that there's a cycle between 1, 3, and 2. And then so here's a cycle. Even though it's completely all connected, there's still a cycle over here. Okay, so maybe we can also, when we are traversing through this, we'll determine if there's a cycle. And if there is a cycle, then maybe we can just return true. So our helper function returns true. And so we know that it is not a valid tree, so our main function will return false. Now, how do we determine whether there's a cycle? Well, let's take a look, right? If we have a DFS call, what do we need a DFS? Well, we need like a visited set, right? Like we need to keep the set of nodes that we visited. And we know that if we visited another node that we've already visited in the past, then there is a cycle. So what will happen here is we'll visit the 0, then we'll go ahead and visit the nodes that 0 is connected to, which in this case is just 1. And now from 1, technically we can visit 0 again, right? Because as I mentioned, it's an undirected graph, but we'll be treating it as directed in terms of the adjacency list. So technically this is possible. So even though this is not a cycle, we'll attempt to visit this. So how can we get around this? Well, maybe like when we are visiting, when you're doing our DFS call, we can just pass in like a parent parameter, right? So for example, when 1 is here, the parent will be 0. So when I'm going through the neighbors of 1, if it is a 0, then I'll just skip over it, right? But for any other neighbor, for example, the 4 over here, I will go ahead and process it. Okay, so let's say we do that. So what happened at this spot? So once we do this, in our visited set, we have the 0, we have the 1, and then maybe here I have my 4. So I'll go ahead and add my 4, right? And notice I'm not popping from the visited set, right? I'm not popping from the visited set. I just want to keep adding on to it because this visited set is going to essentially keep track of all of the nodes that I can visit. So then we'll go back. And then from here, maybe I can go to the 3. So add in the 3. Maybe I can go to the 2 from the 3. So add in this. And notice that when I'm on the 2, I'll try to visit 3 again, but because it's my parent, I won't visit it. But then I'll try to visit the 1 here. And I can actually see that 1 isn't my parent, but I've already visited it in the past. And so what this means is that there's a cycle. So even though we visited all of the nodes here, the second condition here will fail. And so that's how we'll determine that it's not a valid graph. Okay, so let's take a look at how we can do this in the code. And we've done a question similar in the past to determine whether something is a cycle or not. So I believe that question was course schedule. So we'll just take a look at that question. Or take a look at that question if you need a refresher. But let's go ahead and begin. And we'll see like how we can approach this problem here. So I don't actually know about the constraints over here. So I can maybe just return something like if not edges, then we'll return true because an empty graph is also a valid tree. Okay. Now what else do we need? Well, now I want to essentially do my recursive call so that I can determine two things. Well, I want to determine the total number of nodes and whether there are any cycles or not. So I can do something like, for example, let's say we have my helper function. And what am I going to pass in? Well, let's see. In my helper function, what I want to know is I want to know the current node, right? Like one of the nodes. And actually, I guess even before this, we have to create our adjacency list, right? So let's go ahead and do that. So we'll create a list where like 0 goes to 1 and then 1 goes to 2. And the way we do this in Leetcode is we'll import a default dictionary. And I'll have my adjacency list as the default dictionary of list. And then I would do for, let's see, ft. So this means like from to. In edges, then I will create this connection here, which means that the adjacency list of f appends to t, and then something like this. So all this is doing is like, for example, if this was 0, 1, Then here I'm creating the edge that goes from 0 to 1. And then here I'm creating from 1 back to 0. So that's all I'm doing here. Okay, so what do I need? Well, I need to know like which node I'm starting off at, right? So maybe I can just start off at like a node here. I need to know my visited set so I understand all the nodes that are visited in the past. I need to know like my parent to make sure I don't visit my parent again. Do we need anything else? I don't think we need anything else. So let's go ahead and start this and see if we run into any problems. But okay, so what's the first thing we can do? Well, first thing is that like when we first of all arrive in the DFS call, then we know that we have now visited this node. So I can go ahead and add this, and visitor will be a set. So I will add this to my, I will add the node to my set. Okay, so now what? Well, now I need to essentially go through all of my neighbors or all of the items that I'm connected to. So I can do for neighbor in adjacency list at node, right? And first thing I will check is I will check if neighbor is equal to parent, then I will just skip over this, right? Because I don't want to visit my parent again, so I will just continue here. Otherwise I want to see if I can visit this, right? So I can check if neighbor in scene. So if a neighbor is in scene, what does this mean? Well, it means that we visited this neighbor before, but it's not actually like from my parent, right? It's actually not my parent. So what this means is we have a scenario, something like this. Maybe we are at the 2 over here, and I want to see if I can visit the 1, and 1 is not my parent. My parent is actually 3. But here I can see that if I try to visit the 1, then it'll form a cycle. So in this sense here, I will actually return true, and this indicates a cycle. Okay, otherwise what? Well, otherwise I can go ahead and I can visit this node, right? So I can do self.helper, and I'll do node visited. And then what is the parent? Well, the parent is actually just my current node at this point, right? So that's my parent. And so this is all we need to do for this recursive call here. So what can I check? Well, I need to define some variables here. So I will say visited is my set, and I'll pass in a couple of things. So I'll pass in node as 0, and then I'll pass in visited and my parent. Maybe the 0 parent, because for 0, like we want to know what the parent is, right? Even though it technically doesn't have a parent. So we need to define something. So maybe we can just, because this goes from 0 to -1, maybe we can just define this as like -1 here. So like this condition will always be false for 0, because none of the neighbors are -1, so we don't have to worry about that. But what can we check here? So what would this return? Well, this will return whether there's a cycle or not. Now, one thing I forgot to do is like, if we do all of this and we don't ever return true, then we want to return false, because this indicates there is not a cycle. So we can do something like is cycle, and then I can do if is cycle, then I'll return false, indicating that this is not a valid tree. If there isn't a cycle, then I want to determine whether the graph is fully connected or not. So I can return length of visited, which means all of the nodes that I can visit, whether this is equal to, I guess n, is it n here? So n is 5, yeah, 0 or 1, yeah, so 5, it would be 5, right? Because we have 5 nodes. So I guess this would just be n. And so then let's go ahead and run this code. Okay, and I'm getting adjacency list is not defined. I guess I didn't pass it in. Yeah, maybe I'll pass it in at the very end. List. Now let's take a look. What am I getting? Scene is not defined. Yeah, I just call this scene. Well, I call it visited. I always call it scene. Call it scene. Then, okay, so it passes now. Let's take a look. And okay, so what am I getting? So I'm getting 2, and then edges is empty. Okay, so I guess we have to change this condition here. If not edges, and I guess n is equal to 0, then this is a valid scenario, right? Then this is a valid tree. We can also check if not edges. Maybe we can combine this. Let's just do if not edges, and then if n is equal to 0, then we can return true. Else, I guess in this case we would return false, right? Because it means that we are given some sort of edges, but like it means that we are not given any edges, but they're actually nodes. So in that sense, like there is no connection. So we can take a look at that, and just more test cases. So this means that n is 0, and then okay, yeah, I guess that's one more thing. If n is equal to 1, then we want to return true. Why? Because in this case, if there's just a single node, then that single node in itself is a valid tree. So I guess this is the case for like no nodes in tree. This is the case for one node in tree. And this is the case for more nodes. And perfect. So we arrive at the solution. Okay, so what is the time and space here? So the space, if you think about it, at the worst case, if we want our solution to be valid, then we'll visit every single node. So that would be O of n, because our visited scene will be O of n, like it will contain n nodes. And for our time complexity, basically we're going through every single one of these nodes, but we're just kind of visiting them once, right? So assuming it's like the best case, so we're just visiting it like once here. Even in the worst case, we'll just visit it once, but we'll understand that there's a cycle. But essentially, we're just visiting it once. So in this case, it's also like a O of n. You can think of it as O of edges plus vertices, or like just O of n in terms of like the number of nodes. Okay, so that's what we have here. We might actually be able to simplify this, I think, because I don't know like how the edge cases like will be passed in here, but I think we have this, which is fine. So thanks for watching.